Welcome, Math 13 students. I'm going to talk tonight about section 6.1, the standard normal distribution. This is a very specific distribution. There is only one, and we'll talk about the detail tonight. We'll take a look at a couple of different tools, and I'll introduce some vocabulary. We'll flesh this out tomorrow night and practice the keystrokes some more. So, the first notion I want to introduce is one that I brought up in the introduction. Those are the uniform probability distributions. This is where, as I noted last night, all outcomes have the same chance of occurring. And yes, I know I mentioned it last night, but I'm going to mention it again because the notion that it helps me introduce is truly that important. I'm going to have you think of dice tosses. You toss fair dice, you're going to get a 1, a 2, a 3, a 4, a 5, or a 6. That's the sample space. And if the dice are fair, the probability of any particular outcome is equal to 1 out of 6. That's what we mean by uniform probability distribution. It also enables me to graph this sort of distribution. And each particular outcome, very much like a histogram, really that's what it is when you get right down to it. The numbers moved around a little bit like that. I'm going to point out something. The area for that entire rectangle is length times width, or 6 times 1 over 6, or 1. I will also note that the sum of all the probabilities, 6 times 1/6, is also 1. So the notion of area and probability is really pretty much a useful observation. So what we really want to be able to do is to consider area as, and the fancy word I used last night is proxy. Area as a proxy for probability. So we have the area of the entire rectangle is equal to 1. Furthermore, I can use pieces of the area to find the probability of particular outcomes. The probability of either a 1 or a 2. I can find by summing these two areas. So the probability of a 1 or a 2, literally adding those up, just like we did way back when, gives us another way of looking at this. So I like this notion of a uniform probability because it really introduces this notion that, and this is really the important part of it, basically, we measure or calculate probability by finding area. And this is really a fundamental notion that we use throughout statistics. Probability does not exist in the real world. It is not a real thing. It is a human construct. You can't go out there and pick something off the probability tree. It doesn't work that way. So we measure area instead, and we make a relationship or a correlation, if you will, between area and probability. So what does that mean for us? In this particular chapter, we develop tools that we use throughout inferential statistics. But we begin by looking at continuous random variables. And I'll remind people that continuous random variables means the value can exist at any point on an interval. Things like weight, height, time, and there's so many more. In particular, I really need to emphasize that now, because we are looking at continuous random variables, our approach changes a little bit. And in some sense, the tool we use fundamentally changes, but most students don't really let that bother them because it kind of disappears into the background. So let me begin with, and again, I introduced this last night, but I'm going to give this all a little bit more of a look at it. We have what we call the standard normal distribution. And I'll remind people that normal means bell-shaped, if nothing else for us at this point. And the standard normal distribution is a special case of a normal distribution. So that word standard is going to be important. And we already know what the word normal means. We've encountered this word quite a lot. I'll remind people that the normal distribution is bell-shaped with the mean at the top of the hill. The vertical axis is the probability. And believe it or not, this graph, P of X, has a particular formula. It's a crazy formula. Fortunately, our calculator knows this formula very, very well, and it's not hard to utilize. So a normal distribution follows that formula. And if it's not clear, y is the vertical axis and x is the horizontal axis, where you might find something like height or weight or IQ and the like. So that is a normal distribution, and we look at a very special case when we look at the standard normal distribution. And now I'm going to get into that. And I'll adjust that formula, but honestly, our calculator knows that formula quite well. So the standard normal distribution, or the Z distribution, is a normal distribution with the following parameters: a mean of 0 and a standard deviation of 1. So the graph looks something like that. Bell shape centered at a mean of 0. Excuse me. So the mean is 0, the standard deviation is 1. If I'm not clear, that's always when we are working with the standard normal distribution or the z distribution. I use those two terms interchangeably. Now, let's talk a little bit about this particular distribution. And what I am about to say applies to any normal distribution, but I'll put it in context of the z distribution, then expand that a little bit later. So the z distribution provides us with probabilities. So that means the area under the graph and above the z-axis is equal to 1. So that total area underneath that graph, I want to be very clear, is equal to 1. Now, our graph is symmetric. So if I take a look just at, say, the right half, this area in here, this area is equal to 1/2 or 0.5. And since our graph is symmetric, this also applies to the other side of the graph. So over here, oh, look at those colors. I don't know if it's too much. There we go. That area over there is also equal to 0.5. And you can see that if you take the left half and the right half, put them together, you have 1. 1/2 plus 1/2 is equal to 1. So there's a lot of symmetry that goes into this. And again, I can't emphasize this enough. This is for the z distribution with a mean of 0 and a standard deviation of 1. Always. Now, this notion of area applies to all normal distributions. So it applies to, as I say, all normal distributions. let's see, what else can we say about this before I let it go? Yes, I mentioned this in passing last night, but I like to remind people that for the z distribution, and I know I just had it up there on the other page with a mean of 0 and a standard deviation of 1, this right here is a z-score. So it's exactly one standard deviation. So what that means is that for our normal distribution here at 0, as I walk up, as I walk down, and I had this in my notes from last night. A little bit better. These are the standard deviations, sigma. And as I noted last night, the empirical rule applies. So 68% of scores fall between -1 and +1. 2 standard deviations nets me 95% of all my possible z-scores. And plus or minus 3 standard deviations nets me 99.7% of all possible z-scores. And again, this applies to all normal distributions. Right now, we're looking at the z-score with a mean of 0 and a standard deviation of 1. This also makes it very easy to say, convert probabilities into areas. So the probability that a randomly selected z-score falls between -2 and +2 is really calculated by finding that particular area. So I will note that for that particular area, that's plus or minus 2 standard deviations or 0.68. What that means is the probability that we have a z-score between -2 and +2 is 0.68. Now, I know that because I know the empirical rule. What does not work for me in this scenario is any sort of length times width formula. There's no more recourse to that particular notion. So, oh, I said 68%. That's a typo. Bad, Chris. 95% or 0.95. Oh, I suck. There we go. At least I caught it. Thanks for helping me catch that. So there we go. For not yelling at me, I appreciate that. I do apologize for that. But anyway, the idea is that area and probability are now identical. So this is how we like to use this particular process. So consider a random z-score. And I'll pose a question. What is the probability it falls between, and in this case, believe it or not, it makes no difference or not if we include the endpoints. Usually I don't bother including the endpoints here, but in any case, between, let's see, let me pick some weird kind of values. -1.3 and 2.4. Now, here's the real secret to surviving from here on out. The real secret to surviving from here on out is to draw some pictures. The pictures can be very, very simple. I don't grade on the graphing of these kinds of pictures, but the distributions or pictures of the distributions are very important for my students when it comes to correctly framing the problem. So the first thing I do is I draw it. Again, it doesn't have to be a beautiful picture. It should include the mean, 0. It should include the lower part, if there is a lower part, and you'll see some examples, and it should include the upper part, 2.4. So I should draw it. I should then use the appropriate notation. I'm looking for the probability that z falls between, there's a decimal in there somewhere, there too, negative 1.3 and 2.4. Notice the inequality chain from lesser to greater. And what's important here is to note that the probability for that particular interval is equal to this area. So what I need to do is to calculate this area to find my probability. Now, that's a problem to some degree. The reason that's a problem is because I have no direct way to calculate area with a funky shape like that. If I have simple shapes, basically rectangle, triangle, or circle, some other ones, if I look them up, I can use a simple formula. Here I can't. Believe it or not, what we need here is truly calculus. This is a fundamental tool of calculus, finding, or I should say task of calculus, finding area in funky shapes like this. Now, I don't need to teach you calculus, but I just need to teach you how to find that area. And that's what our calculator is very, very good at. So that's the first thing I need to convey. How do we find area? There are a couple of different ways of going about it. So there's a couple of things that I need to consider when I calculate area. First off, as I say, I'm going to need to draw those pictures. But what I'll really need to do is to identify to make sure I've got a normal distribution, and I will need, for that normal distribution, I will need the mean and the standard deviation. Now, old school, we have some tables in the back of the book. I'll be honest, I'm a bit unsure as to why we still incorporate tables in our back of a stat book. Many, many years ago, there were tables of logarithms in the back of algebra books. But then everyone got a calculator and we didn't need those tables anymore. And it's pretty much the same here. I do not use the tables. So old school is really not open to us. We have our calculator. New school is technology, and this we use a lot. So we're going to use our TI-84 to find area or probabilities here. And there are some tricks to doing that. For the TI-84, we use something called normalcdf. normal CDF. I'll show you where it is. You'll see any number of videos of me doing this. In fact, there's a number of these already posted in in my lab courses. But in any case, normal CDF is the tool we apply. Now, what do we need to give the normal CDF tool? We need to give it a couple of things. We need to give it, first, we want to give it the mean, then the standard deviation, then a lower limit, and then an upper limit. And this is part of the challenge when we work with the particular tool. I always need to give a lower and an upper limit. Now, you're going to see me do several different examples here. And in every single case, I am going to draw the distribution. So, we're working for probabilities. We're going to find the probability in the first case, z is between negative 1.3 and 2.4. So, as I said I was going to draw the distribution. Yes, I knew I just drew it. That's okay. I'll draw it again. No harm lost. I'll write my notation, get that all ready to go. So I've got most of what I need for my calculator. I'll need to remember that since we're working with the z distribution, the mean is 0 and the standard deviation is 1. Now, let me go over to my calculator and we'll take a look at how that plays. I'll do it a couple of different times because if I've got my stat wizard turned on, I get a certain look. If I have it turned off, I get a slightly different look. So where are you? There you are. All right, so it's under the distribution key. Now, it's really important that I pick CDF. Believe it or not, we never at any point this semester used the normal PDF tool. So, normal CDF, the lower bound, negative 1.3. Upper bound, 2.4. The mean, 0. The standard deviation is 1. And I can now paste that into, oh, by the way, it's important to remember the order here, lower, upper, mean, standard deviation. When I go back and I do the problem without the wizard on, it's going to need those numbers in the exact same order. So paste, and then I hit enter, and then I get a 0.895 and change. First non-zero number, 3 digits. Look at the fourth, it stays a 5, 0.895. So the 3 significant digits, 0.895. Now, if I've got my stat wizard turned off, and I run through the problem again, normal CDF, now I'll type in a -1, make sure I get the comma. Oh, sorry, backspace. -1.3, there we go, comma, 2.4, comma, the mean comes in at 0, Standard deviation comes in at 1, comma between them. There you go, close them up, and you see the same value there. So you put your limits in first, and then you put in the mean and the standard deviation. So let me go ahead and turn my stat wizard back on. He's a little bit easier to use sometimes. I'll probably turn him off again at some point. Let me stop my sharing for now. We'll get on to the next kind of problem we face here. So let me emphasize this. This probability of 0.895 is equivalent to this area here. So 0.895, 0.895. Now, let's take a look at another couple of examples. And this is where it can get tricky if you're not paying attention. Z is greater than 1. So this time, by the way, I draw these distributions so often for just the basic formulation of my problem that often I just throw them down like that. Greater than 1. There's the 1. So I am interested in that area there. I am interested in the probability that Z is greater than 1. Now, here's the problem we face with this type of question. My calculator needs two distinctly different values. It needs a low value, it needs a high value, it needs the mean, it needs the standard deviation in that order with commas between them. Here's the problem. This particular distribution, this particular question actually has no true upper limit. This graph keeps going out here to positive infinity, and this comes in for a landing and never even crosses that. So there's no value up here that I can put in for down here. That is the challenge we face when we have this type of question. It's the greater than question. Now, here's the way around this. The way around this is just to pick a fairly arbitrary start point and ignore that particular value of area. It's minuscule, utterly and entirely minuscule. Usually I pick a humongous number like 10 to the 9th. That is 1, 1, 2, 3, 1, 2, 3, 1, 2, 3. It's a billion. So that's what I usually use when I have to pick an upper limit. So let me go ahead now and take a look at that on my calculator, and I'll be able to put it in there. Let me clear that. Second distribution, normal CDF. Lower limit, I said it was 1. Upper limit, this is where I'll use the 10, and then I pick my caret key and raise that to the 9th power, 10 to the 9th. The mean is 0, the standard deviation is 1. Let me go ahead and paste that into my function. So a 0.1586 and change. 1586, there's 3 significant digits. The 4th is a 6, the 8's a 9. 0.159. So 0.159. So again, this bit of area and that probability are the same. They really, truly are. I really want to emphasize that. So even though there was a bit of an issue with the calculus, and that is truly what the issue is, we kind of just futz our way through it in some strange way. And I have the same problem when I have calculations where we're looking for values where z is less than. So z is less than, and let's make it a negative 1.9. So less than a negative 1.9. So in some sense, we've got that same issue here, but this time it sort of points off, if you will, to the negative side. So my quick sketch, up the hill, down the hill, there's 0, there's negative 1.9, there's negative infinity, and again, I'm after that little bit of area. We have the probability that z is less than a negative 1.9. And in this case, I use the same idea, negative 10 to the 9th. So I just flip the idea around basically and go with it over there on that other end. Let me share. And back to the distribution, normal CDF. The lower limit this time, and you got to be careful. If you put in a negative, you're going to get an error. If you put in, a subtraction, you'll have an error message generated. You need to make sure you use the negative. Your calculator knows the order of operations, and without grouping symbols or parentheses, in this case, it'll take the 10, it'll raise it to the 9th power, and then apply the negative. That is the first one there. The lower limit. The upper limit is a negative 1.9. Mean is 0, standard deviation is 1. I'll go ahead and I'll paste that in. Normal CDF, and there we go. A 0.02871. 287, the 1 means the 7 stays. And we get a 0.0287. So here again, that area and that probability are the same. Notice that's a very, very small area. I will also note that this is less than or equal to 0.05. So z less than negative 1.9 is a significantly low z-score. So a lot of the stuff that we've been working with still applies, and in some sense it becomes a little bit more solid and visual once you see that. So there we go. Let me go ahead and summarize where we've been so far this evening, because I think I'll be stopping here, and then tomorrow night I'll talk about the second function. the inverse function. So you have the z distribution with a mean of 0 and a standard deviation 1. Area is equal to probability. I emphasize that with the uniform distributions, and you can be guaranteed of seeing one of those uniform distributions either on a quiz or the exam for this material. So just note that the notion is important. Those uniform distributions are also important. So area is equal to probability. The TI-84 tool that we use, normalcdf, with, and in the proper order too, the low, the high, the mean, and the standard deviation. 0 and 1 for the z distribution. That's going to change. It's not always going to be 0 and 1. We can put any values we want in there for a mean and a standard deviation. If we were talking about IQ, for example, it would be 115. 100 for the mean and 15 for the standard deviation. So tomorrow night, I'll talk about what we're going to call critical values and how we find z-scores given areas, probabilities, and contexts. But I don't want to get into that now because I'm not going to have enough time to get through all of that in the way I would like. So let me go ahead and stop the recording.